Okay, how's everybody doing tonight? Good. Still alive, that's good. All right. Okay, so today we're going to talk a little bit about Clipper and Clamper circuits. So we'll start with a review of switch mode power supplies that we talked about last time, and then we'll go into our lecture and talk about Clippers and Clampers. So we'll start off with Clippers. We'll examine what is a Clipper and why they're important, and then we'll do a couple of examples of Clipper circuits. Then we'll talk about Clampers. We'll ask what they are, why do we care about them, and then we'll do some examples of those. And for your lab, no surprise, you get to build a Clipper, a couple Clipper circuits, and a couple Clamper circuits. Okay? I know, right? Shocker. So we'll talk about how you can do that. All right? For homework, there is a couple pages in the lab book that have examples of Clipper and Clamper circuits, and they ask you to figure out a couple things about those. Those are on pages 37 and 38. So you guys can get started on those after the lab tonight. And then if you have any questions about those, or if you want me to do one or two examples, maybe we can look at those. Maybe we can look at one example tonight, and then if you have questions about that, you can ask us next time, okay? And then the next lab we're going to be working on is charge pumps. So I have a reading listed for you on the course outline that is related to charge pumps. So if you go to the syllabus page in Canvas, there's that course outline, and there's a link to take you to a web page to read about charge pumps. Okay? So that is what you can do to prepare for next term. Any questions before we get started? Okay, cool. So let's do a quick review of switch mode power supplies. Remember, we said that we've been talking about power supplies for a while now. We said that the basic components of a power supply are a transformer that takes the high voltage AC and turns it into a lower voltage AC. And then what comes after that? So you're going, remember we're trying to go from a high voltage AC to a flat
Rectifier.
DC line. Yeah, so a rectifier is the next part. That takes the low voltage AC signal and only gives us the positive part of it. And then what comes after the rectifier? Filter. Yeah, the filter, exactly. So that takes the rectified DC voltage, which has big changes, and it smooths it out a little bit. And it's still not a perfect wave, but it's a lot smoother. It's still got a little bit of ripple. And then what is the last component that gets rid of all that ripple? A regulator, exactly. So that's the typical linear power supply. We've been studying that for a while. Last time we watched a video that told us a little bit about another type of power supply, a switch mode power supply. So there were the basic idea behind switch mode power supplies was that they would take an input that was the filtered AC signal that was still had a ripple in it, and then they would increase that and turn it into a several DC output voltages. So they would take that filtered signal that had the ripples in it, and they had a switch that would turn on and off very, very fast, anywhere between 20,000 times a second up to 1,000,000 times a second. So very, very fast switching on and off. And then they would feed that signal through a transformer. And then that transformer can increase the output voltage. And they could have several taps off of that transformer. So you could have several different voltages coming out of that transformer. And then those output voltages were filtered to smooth them out, and then that's how we got the DC output voltages. Okay. So what was an advantage of having very, very high frequency switching? Yeah.
Efficiency.
Yeah, efficiency, exactly. When it was switching on and off like that, it was much easier to filter. So you could use smaller components to do the filtering, and that filtering was more efficient. So you could save size because the components were smaller. You could save money when you were constructing it because the components were smaller, and also it was more efficient. Remember, they said that switch mode power supplies were something like 80% efficient, whereas linear analog supplies were closer to about 50%. So you get a big efficiency advantage. So the more complicated switch mode power supplies that were in that video had that whole transformer arrangement, and they could create several different output voltages. In lab, we built a simpler version of a switch mode power supply. The one we built in the lab was called a buck regulator, or a switching regulator. It would take a DC voltage and then lower it to another DC voltage. So the one we built in the lab was essentially a DC regulator, but instead of being an analog regulator, it was a digital regulator. It was only on and off, so it again had that higher efficiency that we're looking for. Okay, so switch mode power supplies were very efficient when they run, and they're smaller and cheaper to build than analog supplies. So that's why a lot of power supplies are switch mode these days. Okay. So any questions about that? Okay. So then let's go on to the lecture for today. So like I said, we're going to be talking about Clipper and Clamper circuits. So the first question is, what is a Clipper circuit? So a Clipper circuit is the circuit that limits voltage. Or another way to say that is, oops. So a Clipper circuit will limit a certain amount of voltage. If you put a Clipper circuit in line with another part, the Clipper circuit will not allow voltages over a certain level to pass through. So yeah.
So what's the difference between this and like a Zener diode?
A Zener diode would be one example of a Clipper circuit.
Oh.
Yeah. Yeah. We'll see that Clippers use diodes in order to implement their clipping.
Okay.
Yeah. So where is a place that we might use a Clipper circuit? Why might that be important? Well, so we use diodes in a power supply. Yeah. And we could use a Clipper circuit in a power supply. So why might you want to have a Clipper circuit in a power supply? Yeah.
Get rid of ripples.
Yeah, that would be one way to do it.
And a certain voltage.
Right.
So that the signal will be smoother and would have to pass through that much closer.
Yeah. So if you had, say you had some ripples, like this, you could have a Clipper circuit like that, and it would cut off the top part of your ripple. So that would be one example. Yeah. Mm-hmm. Other ideas? Okay. Well, one of the most common places that they're used is in safety circuits or protection circuits. So if you know that, say you've got an expensive piece of equipment, and you know that it can tolerate a maximum of 10 volts coming in. Normally it likes to have its power coming from a 9-volt battery, and it's perfectly happy with that, but it can withstand up to 10 volts. If it gets to 11 volts, then components start to get fried? Well, you could put a clipper circuit at the beginning of the, before your expensive and delicate components, and that clipper circuit can cut off any voltage above 10 volts. And then, so any voltage that was coming in that tried to be higher than 10 volts would just go through this clipper circuit and would not get to your expensive and delicate components. Okay? So
it clips like voltage spikes.
yeah, exactly. It gets rid of voltage spikes. It gets rid of any voltage above whatever level you set. Okay? So safety or protection circuits are common use for clipper circuits. So let's do a couple of examples of clipper circuits. Where's my eraser? There we go.
Compared to fuse, it can hold much higher voltage to protect the.
Well, so
Works at that voltage.
um,
Talking about protection.
yeah, I mean, I think fuses generally are based on the amount of current.
Correct.
Yeah. So if one of the components in your circuit blows out and becomes a short, then your circuit might end up drawing more current than it's designed for, and then the fuse might blow.
So it's only for voltage.
Clippers are only for voltage. Yeah. So the one of the simplest type of clipper circuits looks like this. You might have, say you have an AC signal coming in here, and you've got a resistor, and then diode, and another resistor over here. So this is your load on the right. So this represents your computer that you're powering, or your phone that you're charging, or whatever. This is just a regular diode that's forward biased, but you could imagine you could have a clipper circuit that worked with a Zener diode that was reverse biased as well. So in this case, let's see what happens. Let's say that this was a signal that was 10 volts peak coming in. And let's look at the voltage across the load. So your incoming signal looks like this. It's a sine wave, like this. Let's look at what happens across the load. So let's see what happens when we have a positive voltage there and a negative voltage there. So in that case, we've got a positive voltage there on the diode and a negative voltage there. Is that diode forward biased or reverse biased?
Forward.
Forward. So how much voltage do we have across this diode?
0.7.
Yeah,
0.7.
0.7 volts, exactly. So if we try to have more voltage here coming in, all that voltage is just going to get dropped across this load, and you're only, or I'm sorry, across this resistor, and you're only going to have 0.7 volts across the diode. And the diode is in parallel with the load, so the maximum voltage you're going to get across the load is 0.7 volts. Right? So basically, your output signal would look something like this. This is 0.7 volts there. Now let's look at what happens when we have a negative voltage up here and a positive voltage down there. Yeah, if we do that, right, we've got a negative voltage there and a positive voltage there. So this diode is forward or reverse biased?
Reverse.
Reversed, exactly. So in that case, no voltage or no electricity flows through there. It's essentially like it's not there at all, and we just have that load. So the yeah, so the voltage, right. So in this case, we've got the whole signal between here and here.
For resistance.
So, but you've got some resistance here and some resistance there. Let's say that this was, yeah, say that the load was 1 kilo ohm, and this one was also 1 kilo ohm. That's exactly right. Yeah, then you've got a voltage divider circuit. So,
Negative.
yeah, exactly. So half the voltage is across there and half the voltage is across there. So we said that the maximum was 10 volts and minus 10 volts. Since these two resistors are equal, they each get half the voltage, so they each get 5 volts. So the negative signal goes something like that, where this is minus 5 volts. Okay? Did I go too fast on that one? Any questions? Okay. So, and then this repeats, right? Every time.
Seems like even resistor kind of work as a filter.
Well,
Sort of.
yeah. I mean,
You can't call this good, right?
right. So it reduces the signal, but it doesn't limit it at a particular voltage. I mean, this one always cuts it off at 0.7 volts, no matter what your input voltage was. So the Clipper circuit always cuts it off at a particular voltage. Does that make sense?
Yes.
Yeah. Okay, so that's one example of a Clipper circuit. So you could also, yeah.
This is a question.
Yeah.
If you put another diode in between those two in parallel, facing the other way, would it clip the negative voltage as well?
Yeah, it would. So if we had, let's look at that case. So say,
It's like rail cleaver.
yeah. So we got essentially the same setup here. We've got our resistor and our load over here. But now we've got two diodes. So one is facing this way, and the other one is facing this way. So now you have a maximum of 0.7 volts in both directions. So if you had an incoming signal that looked like this, like we had before, the output would be maximum of 0.7 volts in the positive direction, and also minus 0.7 volts in the negative direction. Okay, like that. Does that make sense? Because one diode limits it in one direction and the other one limits it in the other direction.
It's kind of weird, 10 rules to go to 0.7, so that's what you use the center diode.
Yeah. So
Yeah.
right. So this, I mean, this is an example, right? You could think of this as, so it's drawn as an AC source. We normally think of that as a power source, but it could be another type of source. It could be an AC source that's coming from a radio, And in fact, this type of circuit is often used to protect radios, because radios have very, very big amplifiers inside them. They're expecting very, very tiny incoming signals. So they have amplifiers that really, really increase those signals. So if they got a big signal coming in, those amplifiers could get destroyed. So they normally expect signals in the range of, maybe 0.1 volts maximum. So if they saw something as big as 0.7 volts, that would be about the max that they could handle. So they have a circuit kind of like this that which handles any big spikes that might be coming from this AC source. And this AC source might be like an antenna in the case of a radio. Yeah.
I just have another question about this circuit. If those two, let's just say, were both Zener diodes, like 5-volt Zeners, would it be 5.7? Because one's facing the opposite way?
If they were like this, well, so even if these were Zener diodes, let's see what happens if they become Zener diodes. So say these are 5-volt Zener diodes. Okay. And then you've got your incoming signal, which is still 10 volts peak. Let's say that we had a positive voltage up here and a negative voltage down there. So we've got plus and minus, plus and minus. So is this diode forward biased or reverse biased? Reversed. So, so that would have a maximum of 5 volts across it. What about this diode? Is that forward biased or reverse biased?
Forward.
Forward. So what is the maximum that this one can have across it?
0.7.
0.7. Yeah. So as soon as this one has more than 0.7 volts, it's going to start allowing current to flow through that. So it's going to cut things off.
Oh, so everything would still be 0.7.
Yeah, exactly. So if you have it just like that, everything will be 0.7.
Wow, okay.
Right. But is there a way that you could set it up so that you did have, 5.7 volts?
But it's AC.
Yes, exactly.
Oh,
Yeah, you can put them in series. Yeah. So if you had a situation like this.
1 forward, 1 reverse.
Well, it's AC signal. It's AC signal. The polarity is going to change, and you're going to get 0.7 and negative.
Well, no,
Positive 5.7.
because
Because
they're
either way, you're gonna get the same
Either way, it's
voltage
still,
out.
one was 0.7, so it's going to reduce it down
Oh,
to
yeah, that's right.
Because one will always be forward and one will always be reversed.
yeah.
I'm trying to make it complicated.
So if we have the two,
Oh, I get it.
Yeah.
Yeah.
yeah,
Still think.
Okay.
yeah. So if they're like this,
I'll have to remember that.
Yeah, okay.
all right. So these are each 5-volt Zener diodes. Then when we have a positive voltage up here and a negative voltage down there. So the first one is forward or reverse biased?
Reverse.
Reverse. So how much voltage does it have across it?
5.
5 volts. Yeah. And the second one is forward or reverse biased?
Forward.
Forward. So how much voltage does it have across it?
0.7.
0.7 volts. Exactly. So in this case, you get up to 5.7, and then it clips off there. Same thing up here. And then, right, yeah, when you're negative, right, you got a negative voltage up there, positive voltage down there. So it's like that. So is the bottom one forward biased or reverse biased?
Reverse.
Right, reverse biased. So how much voltage does it have across it? 5 volts. And what about this top one? Forward biased or reverse? Forward. Forward. So how much voltage does that have across it?
0.7.
0.7. Perfect. So again, you end up with a minimum of negative 5.7 volts. Yeah. And this type of circuit is actually used quite a lot in parallel with motors. What happens with motors is that a motor is like a big, it consists of a lot of coils of wire that are electromagnets. But what's another name for a big coil of wire? What type of component is made out of a big coil of wire? Yeah, inductors is what I'm thinking about. Transformers are also. But in this case, just a single coil of wire is like an inductor. And what happens with inductors is that they create big voltage spikes when power is turned on or power is turned off. So when you turn on the power to a motor, it creates a big voltage spike, and then when you turn it off, it creates a big voltage spike. So you might only be supplying 10 volts to your motor, but when you turn it off, that voltage can spike up to 20, 30, 50 volts or even higher.
Also like protection.
Exactly. So you put a pair of diodes like this back to back, pair of Zener diodes, and then that limits the maximum voltage that can happen. So when the motor tries to spike up, that extra energy just loops around through here and goes around in a big circle and wears itself out.
Oh, cool.
Yeah, that actually, that was a problem at a company that I worked for in San Diego. They had designed this robot that had a couple of motors on stages and they moved things around, but the electronics kept blowing out and they couldn't figure it out. And what had happened is they had not put in one of these protection circuits. So every time the motors stopped, it created this big voltage pulse, and some of their components were not rated to handle that much voltage. So this is a commonly used type of circuit, and they actually sell single components that include 2 Zener diodes back to back, just like this. So they sell that in a single package. It just has 2 legs coming out, one from the top and one from the bottom. So it's pre-made that way. Yeah.
The engineers who were designed to rob it probably skipped their Clipper class, right?
It must have, yeah. Well, he was a mechanical engineer, so.
Oh, there you go.
Yeah. Right.
Didn't talk to an automotive engineer, did he?
Apparently not, yeah. So that's another type of Clipper circuit used for protection. Okay. Yeah. So questions about that? Okay. So there are a couple of other types of Clipper circuits that we can look at. So, you can have one where you've got a diode like this, and then you've got another power supply here, which is called a biasing power supply. And it might be, yeah, it's called a biasing power supply. And then your load is over there again. So let's say that this was a 2-volt bias. And again, we've got 10 volts peak coming in. So when we have a positive voltage there and a negative voltage there, we've got positive and negative. So is the diode forward biased or reverse biased?
Forward.
Forward. Perfect. So how much voltage across it?
0.7.
Yeah. 0.7 volts. Perfect. And then we know that this is a 2-volt supply. This is the positive side of the supply, and that's the. So this is always the positive side of the supply, and that's the negative side. So this is always 2 volts across there. So what is the maximum voltage that can be across the load?
2.7.
2.7, exactly. So your incoming, or your positive signal looks something like this. It gets clipped off at 2.7 volts. If this were a 3-volt supply, where would it get clipped off?
3.7.
3.7, right? If it was a 1-volt supply, where would it get clipped?
1.7.
1.7, yeah. So this bias voltage determines where the maximum output voltage that you can have. So if we had a negative voltage up there and a positive voltage down there, then yeah, it's reverse biased. So basically it cuts off that entire path, so it's like that path is not even there. So all of the voltage goes across the load. So if again they were if they were the same resistances, then the load would get a maximum of half of the incoming signal. So it would be something like that. Okay, so those are a couple of examples of Clipper circuits. Any questions about that? Okay. So then, the next thing that I want to talk about is a clamper circuit. Okay, so a clamper circuit is a circuit that, well, let me write down the definition here. So a clamper circuit is one that adds a DC bias to the output. So basically, if you have a sine wave that's coming in, and it looks like this, and it's centered around 0 volts, then the clamper circuit takes the output and modifies it, and it shifts it up or down. So it might end up looking something like this. Okay, same shape, same amplitude, but it just gets moved up, or it could be moved down. So a DC bias is just an average voltage. So it adds either a positive or a negative voltage to an incoming signal. So that's what a clamper circuit is. You might ask, why do we care? Why is that important? Well, next time we're going to look at a couple type of circuits called charge pumps and voltage multipliers. These take lower voltage signals and boost them up to higher voltage signals. And they are based on clamper circuits. So we'll learn a little bit about how clamper circuits work this time, and then next time we'll see how we can use them to take low voltage signals and turn them into higher voltage signals. Okay? So they're useful for increasing the voltage of low voltage signals. So let's look at a couple of examples of clamper circuits. So again, we start with an AC signal. This time we have a capacitor up there and a diode and our load is in parallel with the diode again. So again, let's say that we have a signal that's coming in that's 10 volts peak, and it's an AC signal, so we'll look at the case when, the two cases when we have a positive voltage up here, and then when we have a negative voltage up there. We'll start with the positive. Actually, in this case, it's more instructive to start with the negative case. So we've got a negative voltage up here and a positive voltage down there. So we've got a negative and a positive voltage there. So is this diode forward biased or reverse biased?
Reverse.
Yeah, it's forward biased in this
Whoops.
case because the positive is there. Yeah, so how much voltage do we have across it?
0.7.
Yeah, 0.7 volts. So we started with 10 volts, we have 0.7 volts there. So how much voltage do we have across the capacitor? 9.3 volts. Perfect. So this capacitor gets charged up to 9.3 volts. Okay.
It's polarized.
Well, so, oh, you're right. I drew it backwards. Thank you. Good spot. So it's like that. Thank you. And yeah, this side is more positive than this side. So we have 9.3 volts like that. Now, your incoming signal switches over, and now you've got plus 10 volts there, and ground down there. So now you're at plus 10 volts here, and then this capacitor is still charged up. It's a pretty big capacitor relative to the load, so it doesn't discharge very much across the load. So it basically stays at 9.3 volts. So you start at 10 volts here and you go up by 9.3. So what voltage do you have right there?
19.3.
Yeah, 19.3 volts right there. Okay, and then this is ground. So in that case, we have 19.3 volts across the load. And before, we had the load was in parallel with the diode, so we had 0.7 volts across it. 0.7 volts. So what you get is you start with a sine wave that looks like this, but then it gets shifted up. And so when it's positive, it goes up to 19.3 volts. So this peak is at 19.3 volts. And then when it's negative, it dips down, and the minimum is at, what's this minimum?
0.7.
Yeah, minus 0.7 volts. So that's how it works. That's how it gets shifted up like this. Okay. So that capacitor charges up, and that's what provides this DC offset, this voltage that moves your output up. Does that make sense? Okay. So that's the idea. The clamper circuit adds a DC bias to the output voltage, shifts the signal up. So questions about clamper circuits? Okay. Cool. So then let's do a quick preview of today's lab. For today's lab, we're going to need to create a positive supply and also a negative voltage supply. So we're going to have to use the bench power supplies to do that. But you'll notice that the bench power supplies don't have a negative output setting on them. Okay? So in order to get a negative output, what you want to do is that the power supplies, let's see, you got here. So your power supplies have several outputs like this. In order to get a negative supply, you need to take one of those wires that has 3 cords in it. You'll hook the black cord over there. So this is the negative output, the negative voltage output. The red cord is over there. This is the positive voltage output. And then the green cord has 2 prongs on it. So the green cord one prong goes in there, the other prong loops across to there, okay? Now everybody sees the green cord and they think it should go in the green holes. I know I did that the first time I looked it up. But that's not the way that it works. You put the green cord in the red hole and the black hole. And then this becomes ground. Yeah, exactly. It's two power supplies in series. So what you're doing is you're creating a power supply like that, and then another one like that. And this one is your positive voltage supply. This point right in the middle is ground, and then this one down here is your negative voltage supply. So this is the minus voltage out, this is the plus voltage out, and then like I said, right there in the middle is ground. So if you needed minus 5 volts, you would set this one to 5 volts. Right, so if you call this 0, this is the positive side of the supply and negative. So you call this point 0, then you go down by 5 volts, you end up with minus 5 volts for your negative supply. Let's say that you set this one to 10 volts. Again, that's positive and negative. You start at 0 volts right in the middle. You go up by 10. So what is your output voltage? Yeah. So that's how you can create a negative supply and a positive supply out of two parallel supplies in series. Okay. Okay. So that was one part of the lab preview. What else did I want to say? Oh yeah, the oscilloscopes. Remember, the oscilloscopes have two types of coupling, AC coupling and DC coupling, right? DC coupling shows you the entire signal. AC coupling shows you just the wiggly part of the signal, right? The part that changes. So if you wanted to see a signal like this, and you wanted to see how much it was offset, would you want to put the oscilloscope in AC coupling or DC coupling? DC, exactly. If you put it in AC coupling, it gets rid of that offset for you. So these two signals would look like they were right on top of each other. So you need to put it in in DC coupling so that it shows you the signal exactly the way it is, and you can see that offset. Also, you're going to have one signal on channel 1, the other signal on channel 2. You want to line up the zero levels of channel 1 and channel 2 so that you can see how they compare to each other. See that one is at a higher voltage than the other. Okay. So that's what I wanted to say about the lab preview. Again, you guys remember that there's homework in the lab book and then a little bit of reading for next time. Any questions about what we've talked about today or about the lab? All right, then you are free to take a break, and I'll see you in just a few minutes.